Welcome to this coding walkthrough. Today, we'll explore an interesting problem from LeetCode, problem number 473, Matchsticks to square. This problem challenges us to use logical reasoning and algorithmic thinking to determine if we can form a square using all the given matchsticks. Let's dive in. In this problem, we are given an array of integers called matchsticks, where each element represents the length of a matchstick. The goal is to determine whether we can use all of these matchsticks to form a square. It's important to note that we cannot break any matchsticks, and each one must be used exactly once. If it's possible to construct the square, we return true, otherwise, we return false. Now, the input consists of an array of integers where its length is between 1 and 15, and each matchstick's length can be as large as 10 to the power of 8. The output is a Boolean value indicating whether or not forming the square is achievable. Let's start with an example to understand this more clearly. Suppose the input array is 1, 1, 2, 2, 2. For this input, the output is true. This is because we can form a square with a side length of 2 by grouping the matchsticks into 4 sets, 1, 1, 2, 2, and 2. Each group has a total length equal to the side of the square. On the other hand, consider another example with the input 3, 3, 3, 3, 4. Here, the output is false. While the total length of the matchsticks is 16, which is divisible by 4, the largest matchstick has a length of 4. This exceeds the side length of the square, making it impossible to use all the matchsticks to form the square. Now, let's look at a more complex example with the input 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. In this case, the output is true. We can divide the matchsticks into 4 groups of equal length, resulting in a square with a side length of 8. This demonstrates that even with a large number of matchsticks, forming a square is possible as long as the conditions are satisfied. Speaking of conditions, let's review some important constraints and edge cases to consider when solving this problem. The length of the input array is between 1 and 15, and each matchstick's length is between 1 and 10 to the power of 8. There are a few critical edge cases to keep in mind. First, if there are fewer than 4 matchsticks, it's impossible to form a square. Second, if the total length of all the matchsticks is not divisible by 4, forming a square is also impossible. Third, if the longest matchstick is greater than the total length divided by 4, we cannot create a square. Additionally, if all the matchsticks are of the same length and their total length is divisible by 4, the problem becomes much simpler since forming a square is straightforward. Finally, if the input array contains duplicates, careful backtracking is required to ensure that no matchstick is used more than once while attempting different combinations. These considerations will guide us toward an optimal solution for the problem. To solve the problem, let's start by considering a brute force approach. The idea here is straightforward: generate all possible subsets of the matchsticks and then try to partition them into 4 subsets of equal sum. However, there's an important observation we can make right away. For a square to be formed, the total length of all matchsticks must be divisible by 4. If it's not, we can immediately return false because it's impossible to divide the matchsticks into 4 equal sides. Additionally, each side of the square must have a length equal to the total sum divided by 4. While this approach is conceptually simple, it quickly becomes impractical. Generating all subsets of matchsticks is computationally expensive. There are 2 to the power of n possible subsets for n matchsticks. Partitioning these subsets into 4 groups further increases the complexity. As a result, this brute force approach has an exponential time complexity of 4 to the power of n, making it infeasible for larger inputs. A more efficient strategy is to use an optimized backtracking approach with recursive depth-first search and pruning. Instead of generating all subsets, we focus only on valid combinations. One key improvement is to sort the matchsticks in descending order before we start. By placing the longer matchsticks first, we reduce the chances of unnecessary recursion and can fail faster if a solution is impossible. The process involves trying to place each matchstick into one of the 4 sides of the square, ensuring that no side exceeds the target length, which is total sum divided by 4. If a matchstick cannot fit into any side, we immediately backtrack. Sorting the matchsticks is a crucial step because larger matchsticks are harder to fit, and addressing them first helps eliminate invalid paths earlier. To implement this, we use an array of size 4 to keep track of the current lengths of the sides. This approach significantly reduces the number of possibilities we need to explore. Although the worst-case time complexity is still 4 to the power of n, pruning and sorting make it much faster in practice. The space complexity is n, because of the recursion stack used during backtracking. Another possible solution involves dynamic programming with bit masking. Here, we represent all subsets of matchsticks using bit masks, and a dynamic programming table keeps track of whether a subset sum is valid. While this approach is theoretically sound, it's less intuitive compared to backtracking for this specific problem. The implementation is also more complex, especially when it comes to debugging. Additionally, the time complexity of this approach is n*2 to the power of n, which is slower than backtracking for larger inputs. Given these factors, we opted not to pursue this method further. Instead, we chose the optimized backtracking approach because it strikes a better balance between simplicity, efficiency, and practical performance. Sorting the matchsticks and pruning invalid paths early make backtracking the most effective strategy for solving this problem. At its core, this problem is about partitioning and subset sum, but the unique constraint of forming exactly 4 equal sides makes backtracking the most natural fit. Sorting the matchsticks in descending order is a key insight that drastically improves performance, as it helps eliminate unworkable solutions more quickly. Overall, the time complexity of the backtracking approach is 4 to the power of n in the worst case, though pruning ensures much faster performance in practice. The space complexity is n, which is manageable and primarily comes from the recursion stack. By leveraging these strategies, we strike a balance between efficiency and simplicity, making the backtracking approach the ideal solution for this problem. To solve the problem of determining whether we can form a square from a given array of matchsticks, we need to first understand what makes a valid square. Each matchstick in the array represents a side length, and to form a square, all 4 sides must have equal lengths. This means the total sum of all matchsticks must be divisible by 4, otherwise, forming a square is immediately impossible. The core challenge is then to partition the matchsticks into 4 subsets where the sum of each subset equals the target length, which is the total sum divided by 4. A brute force approach would involve generating all possible combinations or subsets of the matchsticks and attempting to assign them to one of the 4 sides. However, this approach needs careful handling to ensure every matchstick is used exactly once, and invalid configurations are identified early to avoid wasting computational resources. The brute force approach can be broken down into a series of clear steps. First, we calculate the total sum of the matchsticks and check if it is divisible by 4. If not, we can immediately return false. Next, we sort the matchsticks in descending order. This helps prioritize larger matchsticks first, making it easier to identify invalid configurations quickly, such as when a large matchstick cannot fit into any subset. We then initialize an array to represent the 4 sides of the square, each starting at a length of 0. Using recursion, we attempt to assign each matchstick to one of the sides. The base case for the recursion is when all matchsticks have been assigned. At that point, we check if all 4 sides are equal to the target length. If they are, we return true. Otherwise, we proceed with the recursive case, where we try to add the current matchstick to each side in turn, as long as it does not exceed the target length. If adding a matchstick leads to an invalid configuration, we backtrack by removing it and trying the next possibility. If no valid configuration is found after exploring all possibilities, we return false. Sorting in descending order is a key optimization here, as it allows us to address larger values earlier and prevents unnecessary recursive calls. To further refine this approach, we use pruning techniques to improve efficiency. For instance, before adding a matchstick to a side, we check if it would exceed the target length. This simple check prevents redundant recursive calls that would inevitably fail, saving time. Backtracking is an essential component of this algorithm. It allows the program to explore different configurations while undoing invalid paths, effectively ensuring that all potential solutions are considered without duplicating work. In terms of data structures, we rely on a few key elements. The matchsticks are stored in a sorted array to facilitate efficient processing. A fixed-size array of length 4 tracks the current lengths of the square's sides. Finally, the recursion implicitly uses the call stack to manage the exploration of different configurations. When analyzing complexity, we note that generating all possible subsets has an exponential time complexity of O2 to the power of n. However, since we are assigning matchsticks to 4 sides and performing checks during recursion, the worst-case complexity is O4 to the power of n. This is the bottleneck in terms of time. The space complexity of this approach is also worth considering. The recursion stack can grow up to a depth of O(n), where n is the number of matchsticks, as each matchstick is processed one at a time. Beyond that, we use a fixed-size array for the 4 sides and the input array itself, resulting in an additional O(n) space requirement. Certain edge cases must also be addressed to ensure the solution is robust. For instance, if there's only one matchstick, forming a square is clearly impossible. If any matchstick is larger than the target side length, it cannot be included in any valid configuration. If the total sum of matchstick lengths is not divisible by 4, we can immediately conclude that forming a square is impossible. The algorithm also handles duplicate values naturally, as it explores all combinations systematically. To implement this, we use a recursive backtracking function. The function iterates through the matchsticks, attempting to assign each to one of the 4 sides. If a matchstick is added to a side, the function moves to the next matchstick. If, at any point, all sides reach the target length, we return true. Otherwise, we backtrack and try alternative assignments. An optimization we include here is to avoid redundant assignments by skipping sides that are currently at length 0. This prevents unnecessary exploration of equivalent configurations. The main function to solve the problem ties everything together. It starts by calculating the total sum of the matchsticks. If the total is not divisible by 4, we immediately return false. Otherwise, we calculate the target side length and sort the matchsticks in descending order. We then initialize the sides array and call the recursive backtracking function starting from the first matchstick. This function explores all possible assignments and returns true if a valid configuration is found. If no such configuration exists, it returns false. The combination of sorting, pruning, and backtracking ensures that the algorithm is both effective and efficient for this challenging problem. Here, we start by defining a class solution and the method makeSquare, which will determine if we can form a square using the given matchsticks. The first condition checks if the number of matchsticks is less than 4. If it is, we immediately return false because forming a square is impossible with fewer than 4 sides. Next, we calculate the total length of all matchsticks using the sum function. If this total is not divisible by 4, we can return false right away since a square requires 4 sides of equal length. We then compute the target length for each side by dividing the total length by 4. To optimize our solution, we sort the matchsticks in descending order. This allows us to try placing the largest matchsticks first, which can help reduce the number of recursive calls. Finally, we initialize an array sides with 4 zeros to represent the lengths of the square sides as we build them. The backtrack function is then defined to handle the recursive placement of matchsticks. The base case checks if all matchsticks have been placed. If so, it verifies whether all 4 sides are equal to the target side length and returns the result. The backtrack function continues by iterating through each of the 4 sides to determine where the current matchstick can be placed. If adding the matchstick to a side would exceed the target length, we skip that side. Otherwise, we add the matchstick to the current side and recursively attempt to place the next matchstick. If the recursive call successfully forms a square, we return true. If not, we backtrack by removing the matchstick from this side and try another configuration. There's an optimization here. If the side remains empty after removing the matchstick, we can break out of the loop early because trying other sides would yield the same result. If no valid placement is found for the current matchstick, the function ultimately returns false. Finally, the makeSquare method initiates the backtracking process by calling backtrack starting at index 0, which represents the first matchstick. Here, we start by defining our solution class and the method makeSquare. The first check ensures that if there are fewer than 4 matchsticks, we immediately return false since it's impossible to form 4 sides. Next, we calculate the total length of all the matchsticks by iterating through the array. This is critical because if the total length is not divisible by 4, we know it's impossible to form a square, and we return false. If it is divisible by 4, we calculate the target length for each side, which is simply the total length divided by 4. To improve efficiency during recursion, we sort the matchsticks in descending order. This allows us to try placing the largest sticks first, which can help prune unnecessary recursive calls. The sorting logic swaps elements to reverse the array, ensuring we process the matchsticks in decreasing order. After sorting the matchsticks, we initialize an array sides to track the current length of each of the 4 sides of the square. This array starts with all sides at 0. The main logic of forming the square is handled by the backtrack helper function, which we call with the matchsticks, the sides array, the starting index of 0, and the target side length. Inside the backtrack function, we first check if all matchsticks have been placed by comparing the index to the array length. If so, we verify whether all 4 sides have reached the target length. If they have, we return true. Otherwise, we proceed to try placing the current matchstick on each of the 4 sides. Before placing it, we check if adding the matchstick to a side would exceed the target length. If it does, we skip that side. If not, we add the matchstick to the side and make a recursive call to place the next matchstick. Continuing with the backtracking process, once we place a matchstick on a side, we recurse to try the next matchstick. If the recursive call returns true, it means we successfully formed a square, so we return true as well. However, if the placement doesn't lead to a solution, we backtrack by removing the matchstick from that side, undoing the addition. This allows us to explore other possibilities. Additionally, we optimize the search by breaking out of the loop if the current side is empty after removing the matchstick, since trying other sides in the same state would be redundant. Finally, if all possibilities are exhausted and no valid placement is found, we return false. This ensures that the function explores all options systematically while avoiding unnecessary computations, providing an efficient solution to the problem. To solve the problem of determining if these matchsticks can form a square, we start by calculating the total length of the matchsticks, which is 8. Since the total length is divisible evenly by 4, each side of the square must be 2. Sorting the matchsticks in descending order gives us 2, 2, 2, 1, 1, and we initialize 4 sides of the square as 0, 0, 0, 0. The backtracking process begins with the first matchstick, which is 2. We place it on the first side, updating the sides to 2, 0, 0, 0. Moving to the next matchstick, another 2, we place it on the second side, resulting in 2, 2, 0, 0. The recursive process continues to explore further placements. Now, for the third matchstick, which is also 2, we place it on the third side, making the sides 2, 2, 2, 0. For the fourth matchstick, which is 1, we place it on the fourth side, updating the sides to 2, 2, 2, 1. Finally, the last matchstick, another 1, is placed on the fourth side, resulting in 2, 2, 2, 2. At this point, all matchsticks have been successfully placed, and each side of the square equals the required length of 2. This satisfies the base case, confirming that a square can indeed be formed. The output for this example is true. In the second example, we have matchsticks of lengths 3, 3, 3, 3, 4, with a total length of 16. Dividing by 4 gives a required side length of 4. Sorting the matchsticks results in 4, 3, 3, 3, 3, and we initialize the sides as 0, 0, 0, 0. Starting with the largest matchstick, 4, we place it on the first side, updating the sides to 4, 0, 0, 0. Next, we take the first 3 and place it on the second side, resulting in 4, 3, 0, 0. The backtracking process continues from here to explore further placements. For the third matchstick, which is 3, it is placed on the third side, giving us 4, 3, 3, 0. Then, the fourth matchstick, another 3, is placed on the fourth side, resulting in 4, 3, 3, 3. Now, for the last matchstick, which is also 3, we find that there is no valid side where it can be placed without exceeding the required side length of 4. At this point, the algorithm determines that it is impossible to form a square with these matchsticks. The output for this example is false. In the third example, the matchsticks have lengths 5, 5, 5, 5, 4, 4, 4, 4, 3, 3, 3, 3, with a total length of 48. Each side of the square must therefore be 12. The matchsticks are already sorted, and we initialize the sides of the square as 0, 0, 0, 0. Using the backtracking process, matchsticks are placed recursively on the sides while ensuring that no side exceeds the required length of 12. After all matchsticks are placed, the sides are 12, 12, 12, 12, which confirms that a square can be formed with these matchsticks. The output for this example is true. The time complexity of the solution involves analyzing both the sorting step and the backtracking process. First, sorting the matchsticks array requires O and log n time, where n is the number of matchsticks. This ensures that we can efficiently attempt to form the square by starting with the largest matchsticks. Next, the backtracking function explores all possible ways to assign the matchsticks to the four sides of the square. In the worst case, each matchstick could be placed on any of the four sides, leading to 4 to the power of n recursive calls. Although the algorithm includes optimizations, such as pruning branches where a side exceeds the target length or revisiting empty sides, these optimizations don't change the worst-case exponential nature of the recursion. Therefore, the overall time complexity is dominated by the backtracking process, which is O, 4 to the power of n. The sorting step, with its O, n log n, complexity, is relatively minor compared to the exponential growth of 4 to the power of n. Thus, the total time complexity simplifies to O, 4 to the power of n. The space complexity of the solution is primarily determined by the recursive call stack. Since the backtracking function processes one matchstick per recursive call, the maximum depth of recursion is n, leading to O, n, space for the stack. Additionally, the algorithm uses a small auxiliary data structure, a list called sides of size 4, to keep track of the current length of each side of the square. This list requires constant space, or O1. The input array of matchsticks is reused directly without creating additional copies, so no extra space is needed for input storage. When we combine these factors, the total space complexity is O(n) for the recursion stack, plus O(1) for auxiliary space, resulting in an overall space complexity of O(n). Now, let's examine the best, average, and worst-case scenarios for the algorithm. In the best case, if the matchsticks cannot possibly form a square, such as when their total length isn't divisible by 4, the algorithm terminates early after pre-processing steps like summing and sorting, which take O(n log n) time. This ensures that we don't waste time on unnecessary backtracking. In the average case, the algorithm effectively prunes invalid branches during backtracking, resulting in far fewer recursive calls than the theoretical maximum of 4 to the power of n. This makes the average case time complexity much faster than the exponential worst case, though the exact performance depends on the input. Finally, the worst case occurs when the algorithm must explore all possible combinations of matchstick placements, such as when the matchsticks are of similar length, leading to a time complexity of O(4 to the power of n). Comparing this to a brute force approach, which would require O(n) permutations in O(n) to verify each, backtracking with O(4 to the power of n) is significantly more efficient. Mathematically, the backtracking process generates up to 4 to the power of n combinations in the worst case, with the initial sorting step of O(n log n) being negligible in comparison. Therefore, the overall time complexity remains dominated by the backtracking step at O(4 to the power of n), while the space complexity is dictated by the recursion stack depth of O(n). When solving the matchsticks to square problem, there are several common mistakes that can lead to inefficiencies or incorrect solutions. First, not sorting the matchsticks in descending order is a frequent pitfall. By sorting the matchsticks from largest to smallest, you ensure that the larger sticks are placed first, which reduces unnecessary recursive calls and makes the algorithm more efficient. Next, it's crucial to handle edge cases right away, like when the array length is less than 4, when the total sum of the elements is not divisible by 4, or when the array consists only of zeros. Addressing these edge cases upfront saves you from wasting time on impossible scenarios. Another issue arises when solutions attempt to generate all possible subsets without pruning invalid configurations early. This brute force approach results in exponential time complexity and becomes infeasible for larger inputs. Additionally, incorrect management of state variables during depth-first search or backtracking, such as not resetting the state properly, can lead to logical errors or infinite recursion. Lastly, while Python manages large integers gracefully, languages like Java or C++ may encounter integer overflow when summing large values. Always validate and handle the total sum with care to avoid such issues, regardless of the programming language you're using. To approach this problem effectively, it's helpful to think about how these techniques align with what interviewers often look for. Sorting the matchsticks in descending order isn't just a performance tweak, it's often critical for the correctness of backtracking solutions. Interviewers will also appreciate if you frame your solution in terms of constraints, such as verifying whether the total sum of elements is divisible by the required number of partitions, which in this case is 4. If you're comparing different approaches, make sure to explain the trade-offs. For instance, brute force methods may be simple to implement but are computationally expensive, while optimized strategies like depth-first search with memoization offer better performance. Lastly, visual aids are powerful in interviews. Creating a quick diagram to represent how matchsticks form the sides of a square can make your explanation more intuitive and demonstrate your problem-solving clarity. Exploring related problems can provide a deeper understanding of the techniques needed for matchsticks to square. For example, LeetCode 698, partition to k equals some subsets, involves partitioning an array into k subsets with equal sums, which is conceptually similar. LeetCode 39, combination sum, focuses on finding all combinations that meet a target sum, offering insights into subset generation. LeetCode 416, partition equals subset sum, is another related problem involving partitions and sums. Of course, LeetCode 473, the matchsticks to square problem itself, is the best practice for mastering this specific technique. When it comes to alternative approaches, brute force with subset generation is a straightforward method, but its exponential time complexity limits its practicality to small inputs or proof-of-concept scenarios. A more efficient approach is depth-first search with backtracking. By combining this with sorting, you can eliminate redundant computations and improve performance, though it requires careful implementation. This is often the go-to solution for most input sizes. For even larger input sizes or when you need the most optimal solution, dynamic programming with bit masks is an advanced yet powerful technique. While it's significantly more efficient than both brute force and basic backtracking, it comes with its own set of challenges. The implementation is more complex, and debugging can be tricky, especially when managing the bitmask states. However, for problems of moderate to large scale, this approach shines by reducing the computational overhead and achieving excellent performance. Leveraging dynamic programming in this way demonstrates a strong command of both algorithm design and optimization techniques. Great job completing this problem. We covered the importance of subset generation and backtracking, and we emphasized the need to optimize for efficiency in recursive problems. Thank you for watching, and don't forget to like, subscribe, and check out other coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!